Now the lock. And this is the part I want you to take seriously. It's a modifier. Require unlocked, set it false, run the body, set it true. 4 lines. Every V3 fork has it, and most people skim past it. 3 things to notice, in increasing order of importance. 1 security note to carry forward, because it has cost people real money. Initialize is permissionless, and it takes the price from whoever calls it. Anyone can initialize a fresh pool at any price they like. Lending protocols have been burned by exactly this. That's accepted by design. Arbitrage corrects the price quickly. Okay, we've spent 5 episodes writing libraries. Today we open the pool itself, and the very first thing in it is a storage layout that tells you what V3 actually optimizes for. A cold storage read costs 2100 gas, a warm one costs 100. On a swap, storage reads are the dominant cost, not the math, not the loops, the reads. V2 already knew this. It packed reserve 0, reserve 1, and a timestamp into one slot. V3 goes further. 7 values, 248 bits, 1 storage slot. The types were chosen to fit. Add them up yourself. Price is a uint 160, tick is in 24, 3 oracle fields at 16 bits each, protocol fee 8, the lock flag 8, 248 with 8 bits to spare, and that's not luck. The price is a uint 160 partly because Q64.96 needs at most 160 bits for the supported range, and partly because 160 leaves exactly enough room for everything else the swap needs beside it. So when swap starts, it copies slot 0 into memory once, and never pays for those reads again. Now notice something that looks redundant. The pool stores both the square root price and the tick, but the tick is derivable from the price. That's what get tick at square root ratio does. So why store both? Because deriving it costs a logarithm, 2000 gas and change every time. Storing 24 extra bits in a slot you're already writing costs nothing. That's classic space for time, but it comes with a duty. The two must be kept consistent, by hand in the swap loop, and that is an invariant real V3 forks have broken. Next, the immutables. Factory, both tokens, the fee, the tick spacing, and the max liquidity per tick. Written once during construction, then embedded straight into the deployed bytecode. Reading them costs no storage access at all. And the real V3 pool does something strange to get them. Its constructor takes no arguments. Instead, it calls back into whoever deployed it and asks for the parameters. Why go through that contortion? Because create2 addresses are derived from the hash of the init code, and constructor arguments are part of the init code. With 0 arguments, every pool ever deployed has the identical init code hash, which means anyone can compute any pool's address offline from nothing but the 2 tokens and the fee. No registry lookup, no storage read. The periphery leans on this hard for callback authentication, and you'll see exactly how in section 16. We use plain constructor arguments here and rebuild the real pattern with the factory in section 15. Now the lock. And this is the part I want you to take seriously. It's a modifier. Require unlocked, set it false, run the body, set it true. 4 lines. Every V3 fork has it, and most people skim past it. 3 things to notice, in increasing order of importance. First, the flag is a bool inside slot 0, not a separate storage variable like V2 used. The swap is already loading and writing that slot, so keeping the flag there makes locking nearly free. Second, unlock defaults to false, so a freshly deployed pool is locked. Every guarded function reverses until initialize flips it. Initialization is unlocking, which means there's no separate is this initialized, checks scatter through the contract. And third, the auditor's view, which is the one that matters. The lock is load-bearing in V3 in a way it simply is not in most contracts. V3 never calls transferFrom. It verifies payment by snapshotting its own token balance, calling back into you, and then requiring the balance grew by what you owed. So if a callback could re-enter mint or swap mid-flight, a single token transfer could be counted toward 2 different debts. The balance check would pass twice on one payment. That's why every fork touching the callback flow has to preserve this guard, and why lock coverage is one of the first things you check when auditing a V3 fork. That's the kind of reading we do together inside Zealynx Insiders. Live sessions every week on real protocol code and office hours where you bring your own. Links below. 2 more pieces before initialization. First, how the pool learns its own balance. You'd expect a plain balance of call. Uniswap hand rolls a static call instead and checks the return data length. Why? because the compiler-generated version adds an Xcode size check on top of the return data check, and that's redundant here. A token with no code would already fail the data length required. So it's one avoidable check removed from a path the pool hits constantly. And these two functions are the only way the pool ever learns how many tokens it holds. Every payment verification in the protocol, the mint checks, the swap check, compares snapshots taken from them. Second, the timestamp. It returns block timestamp truncated to 32 bits on purpose. The Oracle stores 32-bit timestamps and does all its arithmetic unchecked. So the wraparound, which happens in 2106, cancels out in subtraction. And the function is virtual, so tests can override time. And now initialize, which is the only door into an otherwise locked contract. The caller hands in a starting price as a square root price. The pool derives the tick from it, the greatest tick, whose price is at or below the given one, and writes the whole slot 0 in a single assignment with unlocked set true. The AI require makes it one shot, and notice how cleanly it works. A price of 0 is impossible for a live pool, because the minimum square root ratio is 4 billion and change, so a stored price of 0 unambiguously means never initialized. No extra flag needed, one security node to carry forward, because it has cost people real money. Initialize is permissionless, and it takes the price from whoever calls it. Anyone can initialize a fresh pool at any price they like. Lending protocols have been burned by exactly this. That's accepted by design. Arbitrage corrects the price quickly. But it means any integration that means right after pool creation must not trust the pool's spot price. And any protocol reading slot 0 on a brand new pool is reading a number a stranger chose. Right, 9 pieces. Let's write all of them. The lock, first half. Require unlocked with LOK. Then immediately set it false before the body runs. Order matters here in the obvious way. If you set the flag after the body, the guard does nothing at all. And the second half, after the body completes. Set it back to true. That underscore in the middle is where the guarded function runs. Everything before it is the entry check, everything after is the release. Now check ticks. 3 requires, the same ones you wrote in section 2. Now living in the pool where every position modifying path funnels through them. Lower below, upper. Lower at or above the minimum. Upper at or below the maximum. Verbatim codes. The timestamp. Block timestamp cast down to 32 bits. That truncation is deliberate and it is documented as deliberate. It only works because everything downstream subtracts these values inside unchecked blocks. Now balance 0. Static call the token with the balance of selector and this contract's address. Require the call. Succeeded and that at least 32 bytes came back. Then decode. That length check is doing double duty. It validates the response, and it's why the Xcode size check the compiler would add is redundant. And balance 1, which is the same thing for the other token. Symmetric pairs like this are worth a second look in any audit, by the way. When two functions are supposed to be identical except for one identifier, that's exactly where a copy-paste error hides, and it will not look wrong. Initialize. First, the one-shot guard. Require the stored price is still 0. Revert AI otherwise. And then the whole of slot 0 in one assignment, the price we were given, the tick we derive from it, observation index 0, and the 2 cardinality fields hard-coded to 1. That's the sim where the Oracle will plug in section 13, protocol fee 0, and unlocked, true. That last field is the moment the pool comes alive. Everything guarded by the lock was reverting until this line, and writing it as one struct assignment rather than 7 separate writes is the point of the packing. One storage write for the entire hotpath state. And finally the event, so indexers and the periphery can see the pool's opening price. Let's run it. 15 out of 15. So, the pool exists now. It has a price, a tick, a lock, and a way to see its own balances, which is everything the next 3 episodes need. Next up is mint, where liquidity actually enters the pool, and where you'll meet the callback pattern for the first time. That's the one where the balance check we just talked about does the real work. See you there.